Spectral analysis is a key component of data analysis in a variety of scientific fields, such as electrical engineering, astronomy, and oceanography. So what is spectral analysis? Well, there's a fundamental theorem that says that any time series can be represented as a combination of sinusoidal functions, each function with its own respective frequency. For example, when measuring temperature outside, we know that there's a prominent frequency that corresponds to a shift between hot weather in the summer and cold weather in the winter. But we also know that there's a higher frequency that corresponds to the oscillation of temperature between day and night. By extracting the so-called power at these frequencies, we can gain insight on the physical phenomena at play. In this video, I'll introduce spectral analysis by examining the power at various frequencies when strumming a guitar, and see how things change when I pluck the string at different points. When thinking of frequencies, we often think of different sound pitches. Well, I know at least one person that does, Nobel Prize winner Ray Weiss.
Do the noise for the gravitational wave. The first one did the chirp.
Whoop. Whoop.
Perfect.
Whoop. Whoop.
Perfect. The first one did the chirp.
Whoop. Whoop.
Perfect.
Gravitational wave.
Do the noise.
Whoop. Gravitational wave. Whoop. 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 Whoop.
Perfect. Do the noise.
Whoop. 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 Whoop.
Perfect.
So we basically have NumPy and Matplotlib as normal. I have a number of functions here from SciPy today, including some stuff with wave files and signal. These will be useful for opening data. I've actually recorded guitar audio that we're going to open up and look at. I import this function periodogram. They have a function in SciPy for computing periodograms, but I'm going to use this word in my video, periodogram, a few times. And so what I really want to denote this as is a periodogram function. It's a function that takes in data and it computes a periodogram. And of course in my videos, every time I have _f, that means that it's a function. It takes in something, it returns something. A number of things from the Fourier transform library of SciPy. By the way, if you haven't seen it, I highly recommend watching my Fourier transform video before checking out this video, because I think it'll give all the necessary fundamentals for really understanding spectral analysis. So I'll import these. And so the important thing to note about this video is that what I'm considering, the treatment that I'm considering of time series, is a deterministic one. So it says that I have an x of t that I measure, and I know that that's my process, right? It's not a statistical one. A statistical one would say I've measured one x of t. What does that tell me about the real process that's going on? It's like the difference between, I measure the heights of 100 people in the population. So my sample is 100 people, and maybe I'm only concerned about those 100 people, and I can compute statistics about them, right? Or I want to know, what do those 100 people tell me about the entire population? And my sort of side on this video, the way I'm treating time series, is I'm only interested in those 100 people. So I'm considering just that time series that I've measured, and I don't care about some population thing that it represents. So this is a deterministic, I would call it, I guess, treatment of functions, because I'm not treating them as random variables. If you are interested in treating them as random variables, there's this book I have here by Donald Percival. It's backwards in the camera, of course, but Spectral Analysis for Physical Applications. I'll put a link in the description, but it's a fantastic book. It did take a little while to come. I think it's kind of hard to get your hands on. I think it took about a month or two after I ordered it, but great book. So what we're going to talk about in this video is the power spectrum, right? And in order to understand the power spectrum in somewhat of a mathematically sophisticated sense, we sort of have to go to the basics here of functions. So any time series that you measure is technically continuous, right? But you sample it discretely, but really, it's continuous in time, right? If I'm talking, the molecular vibration of my voice or the amplitude of that is continuous, but I can sample it using a microphone at 48,000 times a second or whatever microphones do, and that's discrete. And so we'll talk about continuous functions first. So there's a theorem that says that any continuous function x of t, so t is time, or it can be any variable, can be represented by an infinite linear combination of complex exponentials. And so what does that mean? Well, in a vector space, we can form any vector using a finite linear combination of unit vectors, right? I can give like 2x hat plus 3y hat plus whatever, and I can get any vector I want in a three-dimensional space. Now, here I'm talking about an infinite linear combination of complex exponentials. So in a vector space, I would, sum together things, but an infinite linear combination says that, well, x of t, rather than being composed of like 3 unit vectors, it's composed of infinitely many points at every possible time there is. There's a sort of different independent variable there, just like a different independent axis in 3 dimensions. And so I need to represent this as an infinite linear combination, and the complex exponentials are like my unit vectors. So you can think of this integral as like a sum. This complex exponential is like a unit vector, and a of f is like the magnitude, like 2x hat plus 3y hat, 2 or 3, those are the magnitudes. A of f is the magnitude. And I denote like sort of the position in that infinite sum by f, and f is a frequency. So this is one possible representation. This is a representation of a function treating it like a vector, and this is one possible basis. So these are like your basis unit vectors here. They're complex exponentials. Of course, there are other ways to represent a function as well using other basis vectors, but for the power spectrum, we're really interested in the amplitude at these basis vectors. Now, when a time series is measured discretely, it means we don't measure it at every time. We're only measuring it at certain, times spaced apart from each other. So I'm going to call that x of tk, where tk is k times delta t, and k is an integer. So you're measuring sort of equally spaced apart. Now, here's where things get interesting. If the time series is band limited to minus 1 over 2 delta t is less than f is less than 1 over 2 delta t, I'll talk about these in a second. These are the Nyquist frequencies. So that means that there's only amplitudes in this integral here if f is greater or less than these values here, or if it's outside those, then it's 0. So this integral, rather than going from minus infinity to infinity, it just goes from this to this. You can write it like that. So here, because a of f is 0 outside these values, I can express the integral like this, and I have e to the I 2 pi f tk a of f df. And now, and 1 over 2 delta t is the Nyquist frequency, and I'll talk about this. There's a significance to this frequency, and it screws up your measurement if you don't take this account or if you're not under this condition here. So this a of f, like I said, is the magnitude of the unit vectors, where you can think of e to the I 2 pi f tk as like a unit vector. You have infinitely many of them, and you construct them, you add them together in this integral to make the function. If I square this, I get s of f, and this is what the definition of the power spectrum is. The square of these amplitudes here, by the way, a of f can be complex in general, but the square of it, the modulus squared, which is a real number, s of f, is the power spectrum. So it measures the power at a certain frequency. So you imagine that your function, these things are almost like sine waves, right? They're not quite, but they're complex exponentials. You could think of them like sine waves. And a of f tells you how much of that frequency is going on in your function, right? So you could have maybe a long sort of sine wave process, and then like something like this is a higher frequency as it oscillates more often. And your function is composed of all these different sine waves of different frequencies, and this tells you how much of that frequency is present in your time series. So for example, my voice would be composed of, there's a few frequencies that are pretty dominant, and so whatever frequencies those are, the a of f's would be larger at those frequencies. Now, if x of t is real, which of course is the case for us, then it turns out that the power spectrum is symmetric, so we really only need to consider the positive frequencies. Now, I sort of glossed over Nyquist frequency, and I think a lot of people do, and it was actually in this book, the Spectral Analysis book, that I really learned what Nyquist frequency meant thoroughly, and so I thought it would be a good idea to include in this video. So suppose that our signal is not band limited to, the only positive frequencies are within the Nyquist frequency range. So what that means is that in our measuring device, which samples every delta t, maybe delta t isn't, short enough to pick up on really high frequencies. There's stuff going on in between. Well, then x of tk can also still be written as this integral from -1 over 2 delta t to 1 over 2 delta t. So we can choose the same bounds here, but all of a sudden we have this a prime of f. So we don't have a of f here anymore. We have a prime of f, where a prime of f is this sum across all these different intervals. You'll see what I mean by this in a second. The main point is that the spectrum that you measure, right, is the modulus of a prime of f squared, and this isn't equal to s of f. And so this is known as aliasing. And so I'll give an example here. So, by the way, suppose that delta t is equal to 1 here. So my Nyquist frequency is at -0.5 and 0.5. These are what these lines represent. And suppose I have a of f that looks like this. And this is the frequency on my x-axis and a of f here. Well, you have to ask, what do I actually measure, right? Because this is how x of tk is expressed. If I measure x of tk, no matter what, it's going to be expressed like this, and I'm going to measure some a prime of f when I do some operations on it, right? So a prime of f has all this folding in that's going on, right? So what it means is that, the intervals go from -1/2 to 1/2, and there's another from 1/2 to 1.5, 1.5 to 2.5, and the same thing on this side. So it's always equal. The width here is 1. It's 1 over delta t, but delta t is 1 here. So these are my sort of intervals here. And when I'm summing across a f plus k over delta t, it means that, this thing here, right, this is somewhere in this interval, but it folds into this interval. Because no matter what frequency I'm looking at, it has the contribution of all these intervals folding back into it. That's how you should interpret this formula here, is that my a prime of f has, contributions from all these intervals folding back to it. So what does that look like? We'll simulate what a prime of f looks like on the plot. So this discrete time series, if I measure with a delta t that gives these Nyquist frequencies here, you can see that obviously I measure the blue here and the blue here, but things are folding back inside, right? So this little guy here, the blue thing here, folds in to make this here, right? And this guy here, he's folding in to make this here, I'm pretty sure. And I have this peak here, and this is folding in on top of this one to make another peak here. And you might think, well, what if I consider a different frequency range? Well, this happens in all ranges too. Not only do all these fold into this one, but if I consider this range, all these fold back into this one as well. So no matter what frequencies I consider, I get this effect. So if I don't sample fast enough, I'm going to measure a spectrum, which is related to this, that has, too much power at certain frequencies. And it's because I'm getting contributions from much higher frequencies that I'm sort of subsampling. So there are different ways to estimate the power spectrum, right? And these are denoted S hat. These are like estimates of the spectrum S of F up here, right? We want to estimate it. We measure a time series. How do we get it, right? And so the most obvious one is the periodogram. And it's given by S hat P. P means periodogram of F is equal to delta T times the discrete Fourier transform of X of TK. These are the sampled points. And it's a function of f, and I square it, and I divide by n, which is the length. And dft is the discrete Fourier transform. Well, it's easy to compute, but it actually doesn't give the true power spectrum at all frequencies. You can show that sp of f is equal to the true spectrum convoluted with this function here. So I can't look at it for just any frequency because it won't give me the true value. But at certain frequencies, known as the Fourier frequencies, when I sample, right, so delta t is my sampling rate, n is the total rate, and then n is a little integer. At these Fourier frequencies, the convolution approaches a delta function, and if I convolve any function with a delta function, I just get that function back, and so I don't have any bias. So, we're lucky because that's actually what the discrete Fourier transform does. It only returns the Fourier transform at the Fourier frequencies. So when we use Python to compute, spectrums and stuff, or to compute the discrete Fourier transform, it's only returning the transform at these frequencies anyways. So we don't need to worry. So the periodogram is equal to S of F at the Fourier frequencies. All right, so let's load in some of the stuff that I've played here on the guitar. So I have a wave file that I've saved. It's in the data here. And what it does is when I use this SciPy wavefile.read, it returns the sampling rate, which I'm going to need if I want my frequencies, and the data, which is essentially the amplitude of the sound as a function of time, right? And it returns like a left and a right ear. So if I just open this and I look at data, it sort of returns like a left and a right. I think this is common for audio devices, but it turns out to be the exact same. So I only take one of the columns. That's what I'm sort of doing there. And then my times of my time series is 0 to the length of data, 1, and I divide by the rate. So if I'm sampling at like 48,000 times per second, it just keeps the delta t small. And so I have my times, which is my time, like this. And if I look at the rate, I think this is a common sampling rate. So 48 kilohertz is what you typically get for most audio devices, or the mic that I'm using right now, which is what I use to record as well. And so I'm going to define some points because I recorded a bunch of notes at once. So these are little like cutoffs that separate it into different notes. And that's what I do here. I make these black lines at all the cutoff values. So this is like low E. I mute the low E, then I A, mute the low A, D, G, and then B and E. So all the notes on the guitar. So here I defined note names. I have a low E, a muted low E. By the way, a muted low E means I put my finger, just rest it on the center of the guitar string, and I pluck, and I'll sort of show you what that does. I play a low E like this, right? And I get all my frequencies. To mute the low E, I put my finger at a antinode, which is a place that goes up and down. It oscillates up and down, and I don't get that low frequency anymore, right? Here's without, and with it. So it removes that fundamental frequency. And I wanted to test this. And on a periodogram, you can see the power at all the frequencies. And of course, the guitar, most of the power goes to the harmonics, right? So the first fundamental mode, the second, and you get these little peaks in the power, which is what we're going to see. So then what I do is I extract all the notes that I have here. So I go between this value and this value. This gives me my low E muted, A, and all the other notes, right? So I'm just going from one value, one line to the other line. And I'm using just a for loop here where I do a little trick. So if all these lines are all my cutoffs as particular integers in the array, I just index every second one. So this one, this one, this one, this one, this one. And then every second one starting on the first one, and I go from sort of one to the other. So it goes from this to this, then it goes from this to this, and it does that sort of cleverly here. If you're interested, you can explore the code a little bit more. And then I make a dictionary that gives the note names and the notes, right? So if I want a particular note, I just go to my note dict, and I go E, and it will return the time series just in this little period here. This function here is just to plot the waveforms of all the notes, just to make sure that I've sort of sampled them correctly here. So I make a 2x5 plot, 2 rows, 5 columns, and I select the axis that I want to plot on, and I plot the ith note, right? So there's 10 notes here, or 9, and I just iterate through. I take, I will just give whatever order that is. I set the title equal to that name, and I want to set the axis off just so there's not a lot of clutter. And I can look just at the waveforms here. So here's my E, my muted E, my A, my muted A, D, all this fancy stuff here. And what we want to do is we want to compute the spectral density, or I'm going to call it the power spectrum because that's what I've been using for the rest of this video. Power spectrum. estimator known as the periodogram, which is what I discussed earlier. So what we're going to do is we're going to take the discrete Fourier transform of this. We'll multiply by delta t, divide by n, and we should get the periodogram. And what we expect for a guitar is that we're going to have peaks in the amplitude of the frequency, or lots of power at the harmonics, because that's the more natural place for the string to vibrate. So I compute the periodogram just using this formula exactly. I take the Fourier transform of my time series, right? I take the absolute value, then I square it, and I divide by, well, delta t is 1 over the rate, so I can also just divide by the rate times n, which is the length of that time series. And to get my corresponding frequencies, right, this is really important, because if I just compute the periodogram, it has no information about what my sampling rate was, right? Other than this, I'm dividing by it, so it's a scaling factor, but if I were to plot it, there's no information about the frequency really encoded in this. And so to get the frequencies, my x-axis, which I'm going to plot it against, my frequencies, I give how many points there are in this time series, but then there's still not the information about the sampling rate, and d gives what delta t is equal to. So if the rate is 48,000 times a second, 1 divided by 48,000, that gives delta t. And this gives me my exact Fourier frequencies here of the periodogram. And so my guitar was slightly out of tune, so the fundamental frequency was about 81.2 hertz. I'm just going to write that down. And what we're going to do is we're going to plot the periodogram, which is what we have here. We have periodogram, and we have the frequencies, and the harmonics of the guitar. So that's n times the first frequency. So I know a low E, at least in this case, when my guitar was out of tune, was 81.2. And we're going to make 10 lines. So 81.2, then 2 times that, then 3 times that, then 4 times that. Those are the harmonics. And we should see spikes in the amplitude, in the power spectrum at those frequencies. So here I plot all these different lines. By the way, this is a really easy way if you want to do a bunch of vertical lines on a plot. You can just do list comprehension. So I go in a list, plot.x vertical line, this times I for I in range 18, and that'll make 18 different lines. It's easier than writing a for loop to do it. And so I plot it. I plot, by the way, I use FFT shift on my frequencies. That's because the frequencies that it returns actually start as positive, and then eventually they go to negative frequencies. It's a weird way about how things are returned. So FFT shift will shift it from going from, in this case, according to this, it will go from -1/2 to 1/2. The way that it normally returns it is it will go from here up to the positive Nyquist frequency, down to the negative Nyquist frequency, and then back to 0. And FFT shift just makes this all in order. So when I plot, I make sure to shift both my frequencies and my periodogram. Then I set the x limit. I only want to consider positive frequencies anyways. So 0 to 2000 hertz in this case. And I plot it, and sure enough, I get these spikes in my power spectrum at these harmonics. So indeed, when I play the guitar, most of the power in the frequencies comes from the fundamental node, the sort of second harmonic, the third harmonic, which is like 3 sine waves. It's basically all the sine waves that you can fit in the 2 connected ends at the guitar. This is common first year physics stuff, right? And so I get all those power at those harmonics. Now, instead of doing this and going through this and using FFT shift and all this gross stuff, there's actually a function that, of course, I imported that can give you the periodogram, and it gives the frequencies as well. So I just use this periodogram function, which I imported. I give the note. This is a time series. I give the sampling rate as rate, and I'm not going to use this, and I'm not even going to consider that in this video, but that's more something you consider with statistical stuff. And I can plot it, and it should give the exact same thing, right? So I have my frequencies and my periodogram. By the way, this thing here, window equals Hanning. So what this window here does is it modifies the time series to avoid excess variance if you're considering a statistical thing. And it will actually give a slightly different result here. But of course, we're not considering a statistical process. We're considering an absolute note that I've measured. So this actually isn't important in this case. And I get my periodogram that looks like this. Now, I talked about muting the E, right? Where I put my finger in the middle, I showed myself playing it, and it sounds higher. And what that does is it technically removes all these power at these frequencies where you have an antinode at the middle when I pluck my guitar, right? So, of course, on a sine wave, when you pluck a string, these are going up and down like this. Any place that remains constant is a node. So by putting my finger in the middle, I'm forcing it to be a node. So I can't have this going up and down. I can't have my first, I can't have my third, which looks sort of like this, and all the odd harmonics, I guess. I only allow for these even harmonics like this. And so what I expect is that I should get 0 power here. And of course, I look at my muted E, I compute the periodogram. By the way, P now will refer to periodogram and F will refer to the frequencies. And I can plot this. And you see that sure enough, these black lines at all the harmonic frequencies, I get no power here because my finger is enforcing. It's like saying, if you think of my guitar as a system, I'm making my system such a way that it can't possibly have power at those frequencies. My finger is absorbing it by resting there. Now, sometimes it makes sense to smooth the spectrum using a convolution. Again, this is something that's more important when you're considering statistical processes to make a smooth spectra, and you can convolve it, right? And you can plot a smooth spectrum, and it sort of removes this variance here. This is, in our case, this is noise, so really this stuff going on in the middle is a statistical process. But again, it doesn't really matter. We're considered mostly just the peaks, and so we don't really need to worry about this. But again, when you're considering the statistical stuff, this is very important. Now, what I really want to consider that's really interesting is the decay, not of frequencies. This is a horrible title. The decay of the harmonic power. That sounds pretty cool. Decay of harmonic power over time. So when I pluck a note, right? If I were to just solve the wave equation for a string, that goes on forever. But of course, my guitar gets quieter. And you could see that in the waveforms, right? It starts off kind of loud, and then it decays and gets quieter and quieter. It starts off loud, gets quieter. All these have a similar sort of pattern to them. My question is, are all the harmonics, right? All the power at the harmonics, are they all decreasing at the same rate? You know, are some decaying faster than others? Maybe the first harmonic stays pretty steady, but the higher order ones go down. Are they even all decreasing, right? Do some maybe increase in the middle? There's a lot of interesting stuff that you're about to find out that I was like, whoa, it's kind of cool. And so these are the questions I was asking. So what you can do is you can split up the time series into little intervals, compute a periodogram for each interval, get the amplitude of the harmonic, and look at that as a function of time, right? So I compute a periodogram here. I look at the amplitude of the first harmonic. That's one data point. Then I compute another periodogram in this region. That's another data point, first harmonic. Do that for all the harmonics for this note, and then plot them decaying as a function of time. So I need a few functions here, right? The first thing I need to do is I want to compute multiple periodograms for one time series. TS stands for time series. So the first thing I do is I say T. That's the length of my time series divided by how many times n I want to split it up. So if I have 10,000 points and I want to split it up 10 times, I have 1,000 points, right? So T gives me how many points there are. It's 10,000 divided by 10, which is 10 in this case. P's is going to be an array of my periodograms, right? P stands for periodogram. S just means plural, so it's a list of all my periodograms. And I want the time corresponding to each periodogram. So for example, if I look at this waveform here, and I split it up like this, I'm just going to take the point in the middle as being the time. So I'm going to write that as a list too. So then I compute my periodogram for each region. So F is my frequencies, P is my periodogram. I use the periodogram function, and then I feed in my time series. Remember, I'm looping over I, so the first case it goes from 0 to 1 times t, so 0 to 1,000. The next for loop, it goes 1,000 to 2,000, then 2,000 to 3,000. So I compute my periodogram for each region. And my time, of course, is the I plus 0.5 times t. So this is like 1/2 t. And I make sure to divide by the rate to turn it into an actual time point. Then I append the periodogram that I create into my array of periodograms. And I can return my times, my periodograms, and the functions. Then I have another function, so I can get my periodograms as an array. I feed it a waveform. I get 10 periodograms for each region of that waveform. This function is used to extract the amplitude of each Fourier frequency, right? Because I get a periodogram. The question is, what is the amplitude of a Fourier frequency? It's actually not that simple of a problem. There's a few little things that you have to do here. because you got to get it right at that peak, and sometimes it spreads out over a region, so I have to make sure to take all those values. And so this is sort of a first order way to correct for some of these things that might happen, right? And I'll show you what I mean. Like, for example, this frequency here, if I do set my XLM again, and I know it's around 82, so I'll set it from 80 to 84. Nope. That's because I'm missing my first harmonic, so I'll go 160 to 170-ish. Right, so this is my, this is for the muted E, and you can see that there's actually power at all these notes sort of surrounding it. So I would really want to take the contribution from all these values. So what I do is, first I create an array of my harmonic amplitudes, right? So this gives the amplitude of a harmonic. So what this is going to be is, like, for each periodogram that I feed in of my list of periodograms, I want an amplitude of all 10 of my harmonics, right? If I'm going for 10 harmonic frequencies. And so I loop through all my periodograms, and these are the amplitudes of each harmonic at that frequency. And I loop through all my harmonic frequencies. So now I'm at a given periodogram at a given harmonic frequency, right? So I might be, like, for example, in this region of my waveform, and I'm considering just the first harmonic, and I want the frequency at that first harmonic. Then I loop through all the harmonics in that region. Then I go to the next region of this waveform, and I go do the same thing for all the different harmonics. And so what I do is I consider a range of my periodograms, and that's specified by this parameter epsilon. So I consider my periodogram where my frequency is greater than the harmonic frequency, so say it's 82, minus epsilon and the frequency plus epsilon. So it gives a little range to consider. So I'm not considering just one peak, I'm considering a range of values. So that's the range of the periodogram that I'm considering for a particular harmonic frequency. Then my amplitude, which of course in some cases is going to be a combination of many of these things, I take as being the any values of the this range, right? So I have a range that I'm considering. I sum together all the values of that range that are greater than the max range divided by A, and A is equal to 100. So what does that actually mean? So for example, if I'm considering this region here, I take the max value and I'm summing all the values together here that are greater than whatever this max value is, 2 orders of amplitude less. So if this was like 10 to the 7, I would be summing over everything that's greater than 10 to the 5 in that range, and that gives me the power at this peak. So that's a little trick way to get around the fact that it's not just at one peak. There's a little bit of a distribution. That's probably due to the guitar, right, not necessarily being constant length, and so you have a little bit of variety in your Fourier frequency. So I sum all those points together, and I append that to my amplitudes. So then I'm still in my first periodogram here, I get all the amplitudes for that first periodogram. Right? And so I append them together, I get all 10, and I append this to the array harmonic amplitudes. So now I have all my amplitudes for my first periodogram, the first region of the waveform. And then I loop through all my periodograms, and I get the first 10 for the first one, all the harmonic frequencies for the next periodogram. And so really this harmonic amplitudes is like a 2D array. So this is my second function. Make sure I define it. Here's a little example of using this compute periodograms function. I get the times, the periodograms themselves, and the frequencies. And so I can get these, and I can plot these, and I don't need to divide by rate here. And so I remove the axis again. So this is sort of like what the periodogram looks like as a function of time here, right? And you can see that it's sort of changing with time. And so then the function here, that the extract peaks, I can plot the relative amplitude of these peaks as a function of time. So that's what I do here. So my harmonic fundamental, by the way, E fund is just a number. It's like 81.2 because my guitar was out of tune. That's my fundamental harmonic. And then I get my time of periodograms, my periodograms, and the corresponding frequency from the compute periodograms function, like I did above. And then my Fourier amplitudes that I get, this is going to be a 2D array because I have 10 amplitudes for each of my periodograms. So they sort of stack like a 2D array. I feed in the periodograms from above, the frequency, and I'm looking at the first 10 harmonics here, right? So it's 1 to 10 times this harmonic fundamental frequency, so 81.2. So it's like 81.2, 162.4, whatever the math is there. And I'm going to consider epsilon range. That's the range of frequencies I consider when I'm around my harmonics is going to be equal to 8, right? Just as a review, that's like in this here. So I pick my harmonic and then I go plus or minus 8. I look for the max value and I take, you know, the values that are specified by A here. So this is for the low E, and it's really interesting because actually when it starts, it's the second harmonic that has most of the energy here, and then it sort of decays, and it's got this weird sort of bouncing behavior, and I'll talk about that a little bit. The first harmonic just sort of has a constant decay, as do all the others, but this one, the second, sort of has this interesting part where it actually gains energy at the end. And I thought, well, maybe this is an anomaly, maybe it's just for this case, but the same thing holds for the E mute as well, right? I get that same bouncing pattern. Now all my odd harmonics, of course, are really low, so that's mostly just noise here that it's picking up on. But the even harmonics, 2 and 4 and all that, are the ones with the most energy. And the second harmonic, right, which is like the wave is sort of going like this on the guitar, it has this effect where it gets stronger and then softer and then stronger and then softer. And so I thought, well, maybe you can hear that. And I think it really is possible to hear. So I'll show you. And listen for it. It gets louder. So if I mute the E and you listen really carefully, if I play it properly, play it with my finger because it's usually a little louder. You can almost sort of hear it getting loud and then soft and then loud and then soft, right? And I think that that's the second harmonic there. So there's an interesting thing going on, right? Anyways, you can see this stuff going on with the other frequencies all sort of decaying as well. And then I thought, well, what happens if I pluck on different positions of the string, right? Because if you do that, by the way, the guitar will sound different. If I pluck down here, for example, it's more of a like raspy sound. And that's more for like if you want to... And you can also sort of play up here and it sounds more gentle, right? This is about a quarter way along the string. It's a little bit of a softer sound. And if I pluck halfway on the string, right, it's a very soft sound. That's because I'm giving most of the energy in this case. That sounds awful. Ooh, it's very deep, right? And that's all the energy going to the fundamental harmonic, because I'm the initial condition of my system, the string kind of looks like this. If I pluck sort of a quarter way through, I'm sort of stretching it where there's a lot of energy in that second harmonic, right? The second harmonic kind of looks like this node and like this in the camera. And so you get more energy there. And then down here, you have all those high frequencies because you're stretching this string right at the end near where it's connected. So my prediction was plucking at these different points, I should get, different relative harmonic amplitude of all my notes. So E1 and E2, E3. 1 is at the end of the string. I keep wanting to say spring. 2 is a quarter way down the string, and 3 is halfway along the string. So this I expect to have a lot of high frequencies. This one I expect to have that second harmonic showing up, and then halfway, mostly first harmonic. That would be my prediction, right? I've gone through this, by the way. It's not new to me. I can cheat here because I spent a lot of time on it. And so I have the my times, my periodograms for each of these 3 positions on the string. And so I can normalize them. So the way I normalize them is important. So I normalize them by normalizing by the magnitude of the first periodogram, right? And that's because the first little bit of the waveform of the note really tells you about how loudly you plucked the string. And I want it to be independent of volume. So that's how I normalize, so I can compare them with each other. So I take this, which is like the periodogram corresponding to the very beginning of the waveform, and I normalize the periodograms like that. And I do it for all 3 of them. Then I can compute the magnitude of the Fourier amplitudes and plot them. And here I plot it. I need to make sure I don't divide by rate here. This is an old bug here. I can plot them. So let's take a close look at what's going on here. So blue is the end of the string, green is the quarter, and orange is the middle. So when I pluck in the middle, actually there's not a whole lot of magnitude in the first harmonic, but it quickly grows and then it sort of decays here. So there's more in the quarter, or there's slightly less in the quarter, and then there's even less in the end of this string. And that's because, of course, I'm giving less energy to that, first harmonic when I pluck farther and farther to the end of the string. And then there's my second harmonic, and you can see that they all have this similar pattern where it sort of bounces like this. So the middle of the string, right, it really starts here, and then it grows, and then it kind of gets louder than the other two notes as a function of time after plucking later on. Whereas these two, the quarter and the end of the string, they start loud and then they decay very fast. So that's sort of an interesting thing to note. A really interesting thing is the fourth harmonic, because the quarter and the middle of the string really don't do anything. When I pluck near the end of the string, you get that similar pattern in the fourth harmonic that you do to the second harmonic. And by the way, I have no idea what this is. Somebody who's smarter than me in the comments can maybe tell me what the heck is going on here with the second and fourth harmonic. What this pattern is, it occurs for all of them here, and then the end of the string for the fourth harmonic. And it looks like there's a corresponding frequency to it. So I'm really curious what that is. And again, it's that thing where you pluck the string and it gets louder and then softer and then louder. And it's like, how is energy added to the system? And it must be being taken from these higher harmonics in some weird way. Of course, all the higher harmonics, they're all decaying as well, but they're more random. And, you can see that the end of the string has slightly more for harmonic 6, for example, harmonic 7. And then these are mostly dominated by noise anyways, just from recording. I hope you enjoyed this video. If you want to see more spectral analysis, maybe even the statistical side of that, let me know and I can do it in a future video. Anyways, like, subscribe, Discord server in the description, and I'll see you next time.